perhaps. It is not completely visible. Yeah, there is not much. Basically, I have a null channel, and I push the transformations for the various hashes on top of it, and then I simply copy the input into this channel, close everything, and then I see everything in the sum array. The transformations were told to store the information in that variable, and the input is basically a self, and that is basically this script we are checking.
Told you. Or but maybe it's just from the lunch. So I mean, it's 12 o'clock. If you guys want to stay and ask Harding lots of questions, feel free. Everyone else, we'll meet back here about 1:30ish. Otherwise,
for memory stick.
Yeah, so remember to give anything you have that you want on the memory stick now, basically to Ron before you go to lunch. And for those who are curious, because somebody did ask, since the internet died on us last night and somebody actually wanted to buy the TDK on the discount, it did expire this morning. That's what they found out. So I asked them to extend it. Apparently they've extended it for a day. So for those of you who felt left out, you can actually buy again. And since somebody else asked, yes, you can buy it from somebody else. We have a rather complex store system. You can purchase 10 licenses and then assign them to 10 completely random people afterwards. So for those with large groups that really need the tools, buy today.
but it's not trying to upgrade, right?
Yeah, it only applies to the new purchase. Okay.
I tried to download and I couldn't get the email to call me back to authorize my new account. I couldn't download. Do you know anything about that?
When was that, today or
last night?
Last night.
I sent an email and I haven't heard back.
I'll follow up on that now that I can actually email myself.
But you got my money.
Good. We'll make sure that's right. Yeah, I'll follow up on that during lunch.
Am I going to get a thumb drive or a CD or anything? Or?
Yeah, you'll.
I don't mean here at the conference. I mean from Active Tickle. Do I get anything, or just?
Not if you order the active CD as well. Yes. Otherwise, it's the download, which. But yeah, it does have to send you the thing to activate your account, and then you have it. So I'll make sure that that's.
Okay. Yeah, that's probably useful.
Yeah. So somebody else has their hand raised for a question for Andreas.
I have one question right there. Did you, what did you have for key exchange in that example?
The key exchange was basically, I put up process ID and clock seconds or something, and the two, both applications take this information, send it to the other, merge it together in some way, mostly Zorin, and that is then the initialization vector for the random byte generator. It is a toy. I haven't seen that yet, but of course, if we had that, is of course better. Yes, and TLS would be even better because it is something not done on your own, but something industry strength.
Yeah, so we're back at 1:30. 1:30. So lunchtime now. Hey, Carrie, can you tell me what email address you're supposed to send to?
Well, I mean, that was give me $200.
Yeah, me too.
It was a good deal without $200. Hey, I already have Safari. Shall I just cancel my Safari?
Do you actually have Safari?
Well, it's, what they're doing is, when I should model the pipe, we're modeling the volume in the pipe, and when you calculate typical flows, there's certain tricks that they use when they're doing square pipes that don't work with the round pipe.
We're going to lunch, so I guess it's fine. But
Making a grid out of basically a round thing is slightly.
Yes, Donald. We would like to have you.
Otherwise, so to have a set of things in your bookshelf, you might not get the dream from. You might have to rearrange your bookshelf.
I have bookshelf stuff.
So, it should work.
I'm putting together a burger run. Yes. All right, now do we have burger and beer?
Yes.
Okay. Well, that's burger and beer. That's what I was thinking.
Where are you going to go for a burger run?
Somewhere close.
Works for me. It's just down the street. Just down the street.
Yes, that's a sweet idea. Actually, we have to repeat it.
Smile. You're on candid camera.
Smile out. We are.
Yeah, just quick again. You never sent you that activation because you created an account.
I thought I had an account already, but you kept saying no. And then I was waiting for the activation.
We're going to Red Robin.
And I don't even get the
Hi. New face.
All right. The round robin expedition will be from the lobby.
People who are not interested in talking but are more interested in drinking, there's room 531. And we got plenty of munchies and plenty of beer, and maybe somebody will talk down there too. And Scott Stewart is going to keep the next session going.
Good afternoon. Welcome back from lunch. Today's afternoon's talk is on applied coroutines. First up is Venkat Iyer, who's got Commits CVXT tool.
Thank you, sir. Welcome back after lunch. Hope you guys didn't have too much beer. I'll try to keep you awake. My slides are a lot less technical than the morning sessions were, at least the ones that I attended. And I hope it's easy on you. So I have 17 slides in all, and I'm not going to read what's on my slides. So you're welcome to look there and read what's there. And my main rules are at the bottom. You can ask questions anytime. And we started about 15 minutes late. And if you have to end on time for call-in, then I have about half an hour, I guess. Okay. So I have about 35 minutes in all. So whenever they kick me out of here, I'm gone. So a quick plug for me and my company. I kept switching education between hardware and software. I did my undergrad in EE, my grad in comp science. I did software for 10 years, and I've been doing the hardware. I've been doing hardware for the last 10 years. My master's thesis was compilers, and still my first love. I like languages very much, and the rest you can read up there. So my company is Common Systems. I've been there for 17 years, and we do everything integral. Everything from our IT to our website to our tools, and of course CVXT is one of our tools.
Quick question, when you say your company, do you own it, or is that just where you work?
Well, short story, I took over as CEO of the company earlier this year, but I'm not one of the founders.
Okay, thank you.
But I joined pretty early on. So CVXT, well, don't read too much into the name. It stands for a verification engine tool. So on the left there is the Verilog simulator. Verilog, for people who don't know, is a It's a hardware description language. It's used to model hardware. That's what you use to describe gates, to describe your DSL modem, or even to describe your PC motherboard. It works at various levels. And it's got an interface called the Verilog procedural interface. And what I'm going to talk about is this green box, which is called CVXT. And that acts as an interface between the Verilog simulation, the hardware simulation, and tests that we write in Tcl. So what I put there on the right-hand side is the user Tcl threads, because what this talk is about the software aspects of this tool. I mean, I can talk about how good this is for verification till the cows come home, but that's not the focus here. Okay, so understand Tcl is not really a hardware forum, though one of the sponsors here is Mentor Graphics, which is an EDA company. And I've just taken a simple example, right? On the right-hand side, you see that's an AND gate, and this is one of probably 300 ways how you can write the AND gate in Verilog. Verilog being one of the languages. So if you think about what this is supposed to be doing, you could think of it as it waits for A or B, one of the inputs to change, then it computes the output, and then it writes the output. All hardware takes time, so there is, even if in the software world, you could write A equal to B and C, and it happens instantaneously. But in the hardware world, anytime inputs change, there's some time taken in the hardware to compute the output, and that's how it gets assigned. And there's various ways to model that delay. Now, each of these blocks here is called a process. Nothing to do with the Unix processes. This is what hardware people call a process. And when you, in a simulation, simulation is when you've written this model for your whole chip or for your whole system, and you're trying to run it. So what's happening is there are all these millions of processes. Think of, like, for example, the last chip that we designed had, 12 million gates. Okay? That translates to 12 million processes running in parallel. Each of these gates is running in parallel. So hardware simulators are sort of operating system kernels. They are event-driven, and they scale widely. That means they can handle a really large number of processes. That's HDL processes. And each of these processes is at any given time, it's waiting for an event or it's waiting for a timeout. I guess you could find an analog for most of this in even operating system kernel. Only this at a real small scale. And of course, hardware simulators, being what they are very good at modeling hardware. So they can handle 12 million, they can handle 300 million, no problem at all. Now, what they're not good at is abstracting this out to a higher level. So, I mean, as I guess in the software world, you could say I could write in assembly, I could write in machine code directly, I could whittle the bits, I could write in C, I could write in C++, I could write in Java, or I could write in, I don't know, UML, pick something. So there's various level of abstract modeling in software which hardware doesn't really have. And most simulators are just getting there. So there have been lots of recent, meaning CVXT predates pretty much every other language there is for verification right now. I mean, you could talk about Cadence's E or Synopsis's, what do you call it, Vera. So there's many languages, and since we were there long before these guys were, we had to invent our own. And rather than invent our own, we just thought, oh, why don't we use something that already exists and we all know about? So that's the reason for using Tcl. I've talked about this many times in the chat, that everybody talks about Tcl dying and Tcl going out of popularity and less people using Tcl. But this one counterexample is in the EDA world, where 10 years ago, I think vSim from Mentor Graphics was probably the only tool that used Tcl. But now, it's hard to find a tool which does not use Tcl, really. I mean, pretty much every tool covering the whole EDA spectrum, right from writing, from place and route to FPGA implementation programs. Everybody uses Tcl as their command language. So my users for this tool are hardware designers, and they all have to use the same EDA tools that we all do. So they all know Tcl to some level, and getting them used to CVXT is one less language for them to learn, because they already know Tcl. This is just a minor shift in their thinking. And of course, since I'm writing my own tool and it's being deployed across multiple company sites, I have users on various platforms, various simulators. In my paper, which is there in the proceedings, you can see a list of all the simulators that we support, and a list of operating systems that we support. But definitely that's one of the challenges for any application deployment. And one of the reasons for using Tcl is that it's well supported across many such platforms. And I'm just going to skip over to the last point there, which is even if everybody comes up with new verification languages, there's things that Tcl can do now that is going to happen only a long time later in other languages. For example, I can easily write a packet sniffer in Tcl. I read a packet off the network, I send it into my hardware simulation, and I read the result out and I can send it back over the network. It's not real time, but imagine having to do this. Well, I guess it's hard for you to imagine, but this is almost impossible to do in any other simulator environment or test environment. And of course, the last point there is the most, I guess, user, the biggest advantage to test writers. Now, what we are saying is CDXT is something that enables you to write Tcl to test your hardware. Now, Tcl test provides a really good way to organize your test, to run selective subsets, to be able to summarize effectively at the end, and it comes with all those built in. Now, so we've been, at Comet, we've been designing chips using CDXT for about 10 years now, and we've used Tcl test, all the versions, and it's been really useful for us. Okay, so since everybody likes to see code, actually everybody really likes to see pictures, but I don't have too many pictures, so I'll just put code instead. So here's an example of how a test would look like when it's running in CDXT. Now, imagine I have a system. Let's say this is your chip that goes into, let's say, your network router, and you have an Ethernet interface on the router. And I write this inside Verilog, which is my HDL, and then I write the bridge, which is CDXT, and I'm writing a test in Tcl, and it's trying to control my simulation so that I can reflect what's going to happen on the chip eventually. One side remark, in designing ASICs, which is what we do, the mask cost is $1 million. That means if you make a mistake, then your cost to redo that is $1 million. Okay, it's not like software. I can't release version 0.0.1 and then next day release 0.0.2. It's version 1.0, and then the next version is 2.0. That's $3 million and 3 months down the road. Okay, so the cost of making a mistake is really high. So verification is a big deal. About 80% of our effort goes towards testing, and 20% is towards the design. So here, I think it's obvious, but I'll walk through it anyway. So I'm going to face the thing so that I can read it as well. Here, this is a Tcl thread that's running as CDXT. So here I can say, there's my interface called Ethernet 0, and there's a signal called error somewhere inside my hardware simulation. I want you to get the value of that. If there is no error, then I want to enable transmit. Then here I want to wait for some time, and we'll come back to that statement later. Then I want to make transmit enable to 0, and then let me explain this again. So when we do here, this statement here is wait for a signal called end of frame. So what this test is doing is it's waiting for the end of frame to be signaled on the Ethernet packet, or it's waiting for a time of 1000. When either of these events fires, it knows that that the test is done. Now, if here it's checking that if it was actually a timer, then it prints this is an error. And wait actually returns either the time or it returns the signal value, which causes the wait to break. But in any case, what this means is at the end of this, this will say either it will error out, and therefore Tcl test will count it as an error, and it will be one of the tests that fail for me automatically. So the interesting part of this wait, when wait happens here, this thread suspends. Okay? Because you're waiting for the hardware simulator to take over now, and the Ethernet packet has to be transmitted. Now, so in the environment, actually, there's multiple user threads. So this is one Ethernet. There could be somebody else who could be doing SATA. There could be somebody else who could be doing something else. And all these threads are running in parallel. And everybody could be sending packets at different times, waiting for different timers. So this wait causes this thread to suspend from what to do. So this is where we get into cooperative multitasking. In hardware, they call it virtually parallel. In software, we call it cooperative multitasking, which is logically speaking, there's multiple contexts running in parallel, but in reality, there's only one running. But you can't predict the order between many of them. Okay. So there's two things here. Was what challenges I faced. One was pthreads and the difference between thread implementations on various platforms, especially Windows. And in earlier cases, I had trouble integrating pthreads versus non-pthread libraries. libc was different in many OSs, and depending on which version of the library got picked up first, it would either load the pthread version or the non-pthread version of many shared libraries, and then I would get codums which I couldn't explain at all. So we eventually moved to using new contexts. We built Tcl with threads enabled, but we not really use threads in Tcl. We just use new context to switch between the various contexts. And on Windows, we just wrote an emulation layer over threads to do the context switching. Now, so obviously that one, you know where it's leading. But the next one is something which I wasn't really proud of, but I've talked about this in the chat many times, and a lot of people thought that this was either not possible or it's a really stupid thing to try. But I've been, but I'll tell you the reasons for that, and I've been doing it successfully for more than 10 years over various versions of Tcl. So the reason for this is that since Tcl is so popular, this guy here, the Verilog simulator, integrates its own version of Tcl. And whereas I don't want to be stuck with that version of Tcl. For example, I was supporting 8.1 till last year, and I'm supporting 8.3.4 this year. I'm still supporting 8.3.4. Whereas I want to use coroutines here. I don't want to be stuck in 8.3.4. So that's one of the reasons I have multiple Tcl versions in one process. One inside the simulator, and one for my CVXT and on my user code. So really, even though I spend probably countless nights trying to figure out what I'm supposed to be doing, this is what it boils down to. I have to use -L, -WL, -B symbolic, and I build well, ignore this enabled threads. I build Tcl shared so that so Tcl thinks that it's going to be loaded into a .so file, but I don't really use a .so file. I use -B symbolic and actually force a link to all the Tcl objects. Now what minus symbolic does is it tells the linker, resolve all the symbols you can now rather than later. So instead of, if it can resolve a symbol later in a .so, it'll try and pull the routine in now. So when I do this, there are only two routines exposed at the end of this. At the end of this in my .cdhd.so, two routines exposed. One is for loading into the simulator, because the simulator is the sort of host process, and the other is actually no, there's only one way. So even though we talked a lot about this, there's just 2 lines of code, and my startup is similar to what the Tcl kit uses. That means when I load up the simulator, I have to do the same thing as what the standard Tcl kit needs to do. So I think Pat would be a better explainer for that. Okay. So enter coroutines. Okay. So when Miguel started. Miguel, okay. My daughter tells me I should pronounce Miguel like that rather than Miguel. So when Miguel started talking about coroutines last year on the chat, I was already drooling. Okay. So this was a perfect fit into what I wanted to do. And I've thanked him many times in chat, and I'd hope that he'd be here and thank him in person, but he's not. But as you saw before, what I'm trying to do is run multiple contexts in parallel, and coroutines are a direct fit into that. So some of the side effects was it actually speeded up my context switches. In reality, performance of the Tcl doesn't really matter, because in my 12 million gate design, when I'm trying to run my verification Tcl, the percentage of time spent in Tcl was the percentage of time was spent in hardware is probably 2 orders of magnitude, it's 1 to 100. So any speed up I can do in Tcl or any slowdown I can do in Tcl doesn't really affect the overall performance of CVXT. But so this is a contrived test. I try to run 10,000 threads in parallel, try to switch between them and try to benchmark it. So it's significantly faster. It also made my build process a lot simpler. I don't have to do uContext and uContext switches and no emulation. And the last one is interesting, which is what I can do now is give the user the possibility of having multiple contexts inside one thread. That means, in the example I showed before, there was this Ethernet thread which was trying to monitor the Ethernet packets. Now suppose I really wanted to send packets and I didn't want to monitor the error signal, but I wanted something to run in parallel which would keep looking at the error signal, and I just want to look at it at the end. So that means what I want to do is let the user have multiple contexts inside one thread, so to speak. Okay. So, and that wasn't really possible before coroutines came. I mean, after coroutines came, that's possible. When I wrote the paper, I hadn't still implemented it. So if you look at the proceedings, you'll see that it's a to-do thing. It's not a to-do thing anymore. It's already done, and it works. Okay. So, what are we doing on time?
10 minutes maybe.
So there are a few slides on how coroutines are used inside CVXT. I'm obviously not glossing over a whole bunch of details here, so just to explain how overall these things work. Okay. So go back. So in reality, there's a coordinator thread here, and I'm using the word threads loosely. Okay, they don't always map into big threads or tickle threads. There's a coordinator thread here, and these are all user threads. And the coordinator thread is sort of passing the baton between all these user threads, or sometimes passing the baton back to the simulator and then waiting for a callback. So this is code that runs in the sort of coordinator thread. So here's how I start a new user thread, and this is hard to read, but let me walk you through this. This is just I create a new interpreter, and for every new thread, so that it has its own context and there's no mix-ups between different threads. And then I alias a bunch of commands, get and put are the two commands that we saw before, and then I evaluate. In this case, just two procedures: wait and start. Which is start is what I do to start the thread off, and wait is what it will do to suspend itself. And then the interesting part is here where I say, okay, in this interpreter, I want you to run this procedure as a coroutine. So this is what really fires off. And here's where the user thread is. It could be a file, it could be anything. So for our Ethernet test, the Ethernet test would have been in a file which was sourced here. So that's how the threads get created. Now this is thread switching. As I said, the coordinator thread is still responsible for switching between the various user threads. So the Ethernet thread started, I did a start, it went off, and it hit a wait. Now when it hit a wait, what it'll happen is it'll actually collect a whole bunch of information about what it needs to wait on, and then return that information back to the main thread. So that comes back as here, okay, which is in the main coordinator thread, it gets called as process. So here, I look at what all the child needed to wait on, and for many of them, I'll add callbacks into the simulator, meaning because the tickle is allowed to wait even for hardware signals, it's allowed to wait for other tickle threads, it's allowed to wait for shared variables, a whole bunch of things. So in some cases, I need to put callbacks into the simulator, and most simulators allow callbacks, which is I can say, oh, whenever the signal changes, call me back, or whenever the simulation time reaches 300 nanoseconds, call me back. So that's this process. Now, I'll come back to this slide if I need to. And so I process all this, and then I just wait. I just return control back to the simulator. Now, the simulator eventually will come back with a callback saying, oh, I got a timeout, so do something about it. So I can get a timeout. I need to figure out which of the user threads are waiting on this particular signal or for this particular time. And then for each of them, I wake them up again. Okay? So this is just thread run args is just, I mean, every time you call the coroutine name again, it continues from where it left off. So okay, so Of course, if I'm using 8.6, I got to use all of 8.6. So I use a whole bunch of DICs internally, but CVXT itself is not object-oriented internally. But we have CVXT is just the lowermost layer. There are a whole bunch of layers written above it, and this is an example of a mailbox, which is you could have multiple tickle user threads running in parallel. And so, for example, I could have a test which says, oh, over the DSL interface, receive 5 ATM packets, then make that into one big Ethernet packet, send it over the Ethernet interface. Now that means that this test has to talk to both the DSL interface and has to talk to the Ethernet interface. And so one of the ways to do that is using mailboxes, and this is pretty typical in most hardware test languages. I mean, if you look at Verilog, if you look at System Verilog, they all have mailboxes. I don't know if I should go into detail over this, but in general, what it is that there's a class, and if you do a get on this mailbox, that means you're waiting for data on it. Internally, it does a wait. That means it suspends automatically, and then whenever data is available, it'll wake up and it'll return the data. So to give you an example of usage. You could think of it as many servers and clients. Each thread is a server or a client. So let's say you're using a PC, and you don't really have a Pentium there, but you have a hardware model there, and you want to emulate the PC sending data out the serial port. So what you have is you write a server for the processor itself, for the Pentium, and it'll accept requests for register reads, register writes. It'll do the request, and then it'll return control back. So that server is my register read-write server. That means that accepts requests and can do reads and writes. So here's an example where I create a mailbox, and then I say, wait for something to be written to the mailbox. And when something gets written, I'll do something in the hardware to actually make the transaction happen. It might be twiddling some wires,